All right, example 5, determine the radius and interval of convergence for this power series. All right, so as usual, we will immediately go to the ratio test, especially since we see that there is a factorial that screams ratio test. So rho is the limit as n goes to infinity of the absolute value of our series term. This right here, which is a sequence. So this ratio. So this is our a sub n, and then we will compute in here the absolute value of a sub n plus 1 over a sub n. Now, since we have these absolute value bars here, this negative 1 to the n term, which really its only purpose is to alternate the sign of all the terms of the sequence here, so that we add them, and it creates an alternating series from that sequence term. So we don't really need that because the absolute values will essentially just make them all positive 1. So we really just need to work with this. So a sub n plus 1 would be x to the 2 times n plus 1 over 2 times n plus 1 factorial. And then divided by a sub n, we'll just have multiplication by the reciprocal. So, quick little things here. X to the 2 times n plus 1 is 2n plus 2, which is x to the 2n times x squared. Down here, this factorial, of course, will turn into 2n plus 2 factorial. So then replacing those items. Now also, since we are going to have the x to the 2n cancel with this x to the 2n, so let's just, they cancel. This absolute value doesn't do anything to the factorial terms because it's just a product of positive numbers, which is positive, so the absolute value doesn't change that. Normally, the absolute value will stay and linger on the x term, the term that has the x in it. But because this is being squared, even if x itself is negative, because it's squared, it becomes positive. So really, this absolute value of x squared is just the absolute value of x quantity squared, which is just, well, same thing as x squared. So really, we can drop the absolute value bars altogether, and we'll have this become x squared 2n factorial, and then we're going to want to split up this factorial here, which we'll do into 2n plus 2, 2n plus 1, and 2n factorial. So we'll just take all those terms. 2n plus 2, 2n plus 1, and 2n factorial. And of course, the 2n factorials will cancel. All right, so what we have now, after that, well, we can factor out that x squared. So we have x squared times the limit as n goes to infinity of 1 over 2n plus 2, 2n plus 1, which this limit is just 0. So then we have 0 times x squared, which is 0. So rho is 0, and because rho, for the ratio test, is 0, we have convergence whenever rho is strictly less than 1. Since rho is a constant and it's always equal to 0, no matter what the value of x is, no matter what the value of x is, this is equal to 0. This means that this converges for all x. So this means the radius of convergence is infinite. So r equals infinity. And again, the reason for this, it can be a little counterintuitive because if you just look at this statement and then look at this statement, it seems like they are complete opposites. That a result of rho equals 0 means a radius of convergence of infinity. Well, again, think about what this is actually saying. What this is saying is that the value of rho doesn't depend on x, because this expression on the right-hand side of the equal sign doesn't contain any x's at all. Since it's independent of the value of x, that means x can be as large or small as it wants to be. And we still have convergence. So in effect, the radius, the radius of convergence is free to be as large as it wants to be. So we'll choose this to be infinity. Okay, so since the radius of convergence is infinite, we don't actually have to test the endpoints of our interval, because if the radius of convergence is infinite, then that means it's all real numbers. And we can't actually plug in infinity for x, so there are no endpoints here. So if you have an infinite radius of convergence, this just implies that the interval of convergence is just the entire real number line.